Yo, what's good everyone? Welcome to Stoichiometry and Solutions Part 6. Today we're going to be talking about colligative properties. So the properties of a solution are going to be different if you have no solute versus if you have solute. And so that's all colligative properties are. Colligative properties are properties that depend on the solute. So the formal definition is that colligative properties are properties of solutions that depend on the concentration of solute molecules. And an interesting thing about this definition is that the identity of the solute doesn't matter. So really all colligative properties depend on is the concentration, not the identity. And there's going to be four main types of colligative properties, and that's freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure. I'm only going to go over the first two because they're really the only ones that come up. The bottom two are also colligative properties, but they don't come up as often. So we're only going to go over the first two, which is freezing point depression and boiling point elevation. Let's start with freezing point depression. So whenever a solution freezes, what's happening is that the particles, the solution particles, are getting closer together. So at the start, when they're in their liquid form or whatever, they start off really far apart, and then in their solid form, they're really close together. Now, if I introduce some solute particles to this, what happens is that as the temperature goes down, the particles get closer and closer together, but the solute particles prevent them from getting as close as they want to be. And that means you have to lower the temperature before you reach your freezing point. So the freezing point depresses, or it gets lower. You need lower and lower temperatures to get the solution to a solid form. And that's because the particles are physically blocking them. And the amount by which the freezing point depresses is expressed by this formula, which is the change in TF equals KF times M times I. So the change in TF is the freezing point depression. KF is a constant. And for most problems that you do, you won't have to know the KF value. It's based on the solvent. But the only one that you might be asked to know is the KF of water. So the KF of water is 1.86 Celsius per molality. And it's important that you know that the M here represents molality. Molality is one of the units of concentration, and it's different from molarity, which is far more common. So molality, remember, is moles of solute per kilogram of solvent. Colligative properties are some of the only uses of molality that you see commonly. And so the M in the freezing point depression formula represents molality. The last bit is the Van Hoff factor, and I want to get into the Van Hoff factor in more detail a bit later. So let's put that off to the side and just see how the freezing point depression formula is used in the context of a problem. So we're told that a solution that contains 55 grams of ascorbic acid in 250 grams of water freezes at negative 2.34 degrees Celsius, and we're asked to calculate the molar mass of the solute. And since we haven't discussed Van Hoff factor yet, I'm giving the value of the Van Hoff factor, which is 1. So let's consider what our strategy for this problem is going to be. We know that the change in TF is going to equal KF times the molality times the Van Hoff factor. Now, which of these values are we given? Well, we're given change in TF, and the change in TF is going to be 2.34 degrees Celsius. And the reason we know this is because we're told that it freezes at negative 2.34 degrees Celsius. Water usually freezes at 0 degrees Celsius, so the fact that it's 2.34 degrees below that means our change in TF is 2.34 degrees Celsius. We also know KF. KF is 1.86 degrees Celsius per molality, and that's from the fact that the solvent that we're using here is water, and the KF of water is 1.86. We don't know molality, but we do know certain parts of molality. We know that molality is moles over kilogram, moles of solute over kilogram of solvent. We don't know how many moles of solute we have, but it wouldn't be that hard to figure out. We know that the moles is going to be 55 grams over the molar mass of ascorbic acid. And the kilogram of solvent is 0.25 kilograms. And the way we get both these values is the fact that we're dealing with 55 grams of ascorbic acid and 250 grams of water. So the solute is the ascorbic acid, and the solvent is the 250 grams of water, which is 0.25 kilograms. and we would have to multiply this value by 1, and because we're told that the Van Hoff factor is 1. So the question asks you to find the molar mass, and using the setup that we have now, all we would have to do is solve for mm, and that would be our molar mass. So once you isolate for molar mass, you'll get that it's about 175 grams per mole, and that is our answer. So the main thing to realize here is that the change in TF is going to be 2.34. That is basically all you really need to. The conceptual jump here is that the change in TF is 2.34, and again, that's coming from the fact that the freezing point rather is negative 2.34, which is 2.34 degrees Celsius lower than it should be. Now, boiling works pretty differently. So boiling works by the fact that when you have a solution and you start heating it up, the particles of the solution move faster and faster, and eventually they gain so much energy that they can just jump from the surface of the liquid and turn into this gas. So when you're at your boiling point, that means that most of the particles have enough energy to jump up from the surface of the liquid and become a gas. But when you introduce some solute particles to your solution, what happens is that the surface of the liquid, the surface of your solution, gets covered by these solute particles. So your molecules of solution need more and more energy to jump up from the top and become a gas. And therefore we say boiling point elevates, meaning you need to increase your boiling point in order for all your solution particles to turn into gas. And boiling point elevation has a really similar equation to freezing point depression. And it's the change in the boiling point elevation is going to be Kb times molality times the Van Hoff factor. And most of these stay the same. So Kb is also a constant, and for water, they happen to be the same. It's 1.86 degrees Celsius over molality. And of course, you have m, which represents molality, and I, which is your Van Hoff factor. So let's do a problem with this. What is the boiling point of a solution prepared by adding 29.3 grams of menthol to 0.0590 kilograms of chloroform? The boiling point of pure chloroform is 61.2 degrees Celsius. The boiling point constant for chloroform is 3.85 degrees Celsius per molality. And we're also told the Van Hoff factor, which is 1. So the formula for boiling point elevation is change in Tb equals Kb times m times I. And two of these values we already have. We know what Kb is and we know what I is. So let's write that down. Change in Tb equals 3.85 degrees Celsius per molality times m, which we don't know, times the Van Hoff factor, which is 1. And again, these are coming from the problem itself. So we're told the Van Hoff factor here, and we're also told the Kb value here. All that's left to do is find molality. Molality is going to be moles of solute over a kilogram of solvent. And one of those values we already know. We know how many kilograms of solvent we have. We know that we have 0.059 kilograms of chloroform. All we have to do is find the moles of solute. Our solute in this case is the menthol, and we have 29.3 grams of it. So to turn that into moles, we need to divide by the molar mass. So we have 29.3 grams of menthol, which is C10H20O, divided by the molar mass. The molar mass of menthol is 156 grams. So 156 grams. And that comes out to about 0.188 moles. So let's put this information together. So we know that the change in Tb equals to 3.85 degrees Celsius per molality times 0.188 moles over 0.059 kilograms times 1. And if you solve for Tb, or change in Tb, it's going to be 12.20, about 26 degrees Celsius. Now, the question asks for the boiling point of chloroform. We found what change in Tb is, and we're going to need to decide whether or not we add this figure to the boiling point or we subtract it. But since we're dealing with boiling point elevation, we're going to need to add this value. So again, what we found is that when you add 29.3 grams of menthol to 0.059 kilograms of chloroform, the boiling point of your solution increases by 12.26 degrees Celsius. So let's add 61.2 degrees Celsius plus let's just say 3 degrees Celsius. Your new boiling point becomes 73.4 degrees Celsius. And that is your new boiling point. So this is all just coming from our formula here. You just plug values in and then you add that total change in the boiling point to your initial boiling point and you get the new boiling point of your solution. So let's move on to talking about the Van Hoff factor. The Van Hoff factor is the ratio between the number of particles present after a dissociation to the number of particles initially dissolved in solution. And an example is if you look at sodium chloride. For sodium chloride, it's going to dissolve into sodium ions and chloride ions when you dissolve it in solution. So the ratio between the number of particles present after dissociation to the number of particles initially dissolved is 2 to 1. So that means the Van Hoff factor for sodium chloride is 2. Sodium chloride is what we call an electrolyte. So an electrolyte is a substance that dissolves into cations and anions and as a result can conduct electricity in that solution. So sodium chloride dissolves into cations and anions. And therefore we can categorize substances into two different categories. So we have non-electrolytes and electrolytes. And as such, the Van Hoff factor is going to depend on whether a substance is a non-electrolyte or an electrolyte. Let's consider the first one, the easier one first. So a non-electrolyte. That's going to be a substance that doesn't dissolve into cations and anions. That means your Van Hoff factor is going to be 1. And this is because if the substance doesn't dissolve into cations and anions, the particles that you have before a dissociation and after a dissociation are going to be the same. So the ratio is 1 to 1, and 1 to 1 is just 1. So your Van Hoff factor is 1. Non-electrolytes are usually held together by covalent bonds, and they're going to be usually nonpolar in nature. If you look at certain examples of non-electrolytes, they're usually these long organic compounds. And these long organic compounds are definitely held together by covalent bonds and they're usually nonpolar as well. So if you do see these long organic compounds, they're likely to be a non-electrolyte and therefore their Van Hoff factor is going to be 1. Let's look at the other type, so electrolytes. You can categorize them into weak electrolytes and strong electrolytes. A weak electrolyte is going to mean that when you dissolve that certain compound, it's only going to dissociate a little bit. And by little bit, I mean about 1 to 10%. On the other hand, a strong electrolyte is going to dissolve almost entirely, almost 100%. And we can take the degree of dissociation and put it to a number. So we say that the degree of dissociation is alpha. So for weak electrolytes, alpha is going to be about 0.01 to 0.1. And for strong electrolytes, alpha is going to be around 1. So we take the percentage and we turn it into a decimal. To calculate the Van Hoff factor for electrolytes, it's going to be this formula. So it's 1 plus alpha times n minus 1, where n represents the number of ions. If you notice for strong electrolytes, your alpha value is 1. So that means I comes out to 1 plus n minus 1, which means that I is basically going to be n. For weak electrolytes, it's going to be far less since your degree of association is between 0.01 and 0.1. Your weak electrolytes are going to be things like weak acids, weak bases, and you can see examples of certain ones here. On the other hand, strong electrolytes are going to be things like strong acids and strong bases, but you also have one other category, and it's going to be salts. And like last time, there's examples here which you might consider memorizing. And that's about it for colligative properties. I'll have a video up later where we do some practice with problems involving colligative properties and especially the Van Hoff factor, because that's by far the hardest part about colligative properties. But other than that, I hope you learned something and I hope to see you later. Thank you.